Okay, so we were talking about the value of information in the last session, and we spoke about how the value of information depends on what use that information will be, whether it will make you change your plan and take another a different preference. So if you do that, then the value of information is more. So now let us look at some of the properties of the value of information. Okay, so we know that the value of perfect information is VPI, right? And VPI, depending on EJ, evidence EJ. So for evidence EJ, VPI has to be greater than or equal to 0. That's the first property that we talk about. So this value is always non-negative, basically. It's always positive, okay? Okay, the second property that we talk about is that it is not additive, right? It is not, we cannot add it in this way. So if we take two pieces of evidence, EJ and EK, and we want the value of perfect information, EJ, EK, we cannot take the value of perfect information for EJ and EK and add them together in general. Maybe it will work in some particular case, but in general you cannot add them, okay? But they are what is called the order independent. So you could say that you could even exchange the order, right? So VPI EJ EK will be equivalent to VPI EK EJ basically. In other words, VPI of EJ plus VPI of EEJ of EK. In other words, you are using this information will be equal to VPI of EK plus VPI of EJ using the previous evidence also. Okay, so we can say that it is order independent. So next we talk about information gathering agent. Okay, so information gathering agent is something like what is given here in this piece of code, right? So what it does is that you are trying to find the value that maximizes the value of perfect information of EJ, okay, given the cost. So you have a cost of EJ. So both these are taken into account, and if your VPI is greater than the cost, okay, then you say that you request for the EJ. Otherwise, you return the best action, you do not take that EJ into account. So this is the information gathering agent we are talking about now. So this gives the overall design basically, okay. So for evidence EJ, we talk about the cost EJ, right? And then we talk about VPI of EJ, that is the value of perfect information, and you see whether the cost is more than the value of getting the VPI. If the cost is more, then it may not be worth doing this, right? So that's what the information gathering agent does basically. Okay. So next we come to the topic of making complex decisions. So we just talked about making simple decisions up till now, maybe taking a single action, but you have a complex decision which may consist of a number of actions moving through a set of states. So that type of thing is called a complex decision, okay. So what we are doing here is that we are making decisions in a stochastic environment basically, and the earlier part we talked about one shot or episodic decisions, whereas here we will talk about sequential decision problems. Okay, so you are taking a sequence of decisions in a particular order. Okay, and the agent's utility depends on a sequence of decisions that are taken. So, what is the sequential decision problem? So, let us consider an agent, okay, which is situated in this particular square or rectangle given over here in the start position, right? And the agent has to move, okay. It can either move up or down or left or right basically, okay. And it has to take a sequence of decisions so that it comes to an output node, right. So that the terminal node rather. So there are two terminal nodes here. This is the terminal node which has a utility of +1 or a reward of +1, and we have the terminal node which has a reward of -1. So these are the two terminal nodes that we have. So how do you move through this? Okay. So that is what this particular problem is basically. So it needs to reach one of the two goal states. Okay. And the actions the agent can take is up, down, left and right. So that is AS or the or actions at a state S. Okay. So we can see here that the best movement or the best sequence of actions would be up, up, right, 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 right. So that is what we are getting over here. So what we say is each action achieves the intended effect with probability of 0.8, okay, but the rest of the time the action moves the agent at right angles to the intended direction. Okay. If the agent bumps into a wall, it stays in the same square. Okay. In other words, if you say left from here, it stays, it just bumps into the wall and comes back into the same state. So we can say if it starts from 1 1, if the action up moves the agent to 1 2 with probability 0.8, but with probability 0.1 it moves right to 2 1, and with probability 0.1 it moves left and bumps into the wall and stays in the same thing. So suppose you use the sequence up, up, right, right, right. Okay. So what is the probability of doing this? 0.8 to the power of 5. Okay. It has a probability of 0.32. There is also a small chance of accidentally reaching the goal by going the other way around. So that will be 0.1 to the power of 4 into 0.8, because finally it needs to reach that which has a probability of 0.32, right. So the B illustrates the transition model. So in other words, it moves up with 0.8, but it can also move left or right with a probability of 0.1. So the transition model describes the outcome of each action in each state. So we can write probability of S dash given S and A as the probability of moving into a state S dash from state S with action A, right. So if you have these probabilities, okay, you can say you have these probability values here, right. You can have these probability values in all these states, telling you how what is the probability of moving from this state to the state with some action, from the state to the state with some action, etc. And you can look at the whole thing as a big 3-dimensional table which contains all the probabilities that we are now talking about. Okay, so we can call this the transition model. But instead of that, you could also represent it as a dynamic Bayesian network. So we know that in the dynamic Bayesian network, some of the values may not be necessary because you find the dependencies. Okay, so what are the parent nodes, etc., will be found, right? So what we say, what it says here is that every square has what is called a reward, right? So if you go to a particular square, you get a certain reward, okay, which can be added on to the utility basically. So the reward is minus 0.04 in all the states except the terminal states, and in the terminal states we know it is plus 1 or minus 1, right? So so what happens is that the negative reward of 0.04 minus 0.04 gives the agent an incentive to reach 4.3 quickly, okay. Otherwise it can just be circling around and then reach 4.3 later, right. So what you have is what is called a Markov decision process, okay. So it's a sequential decision problem for a fully observable stochastic environment with a Markovian transition model and additive rewards, and that is what is known as the Markov decision process. And what does it consist of? It consists of a set of states, okay, out of which you have one initial state, you have a set of actions of course which are available, and a transition model probability of going to state S from S dash from state S with an action A, and you have a reward function RS for every state, okay. So that is what we call a Markov decision process basically, okay. So what you need is some type of a policy, okay. So a policy tells you what are the states that you can go through, okay. A solution to this is known as the policy, okay. And if you have a policy pi, say, and if it is take a state S, it will tell you what is the recommended action for the particular state S by using the policy, okay. And what we want basically is an optimal policy, that is called pi star basically, okay. So we are looking for this optimal policy. So how do you measure the quality of a policy? It is measured by the expected utility of the possible environmental history, okay, generated by the policy. So we want pi star, which is the optimal policy basically. Yeah, so the optimal policy is shown here, okay. So this is the optimal policy for the stochastic environment where RS is equal to minus 0.04, okay, in the non-terminal states. Okay, so you find that a policy has to be got for this, right, and the policy will also depend on the value of RS that you have at the non-terminal states, okay. So if you, depending on the value of RS, okay, you may have different ways of going through this, okay. So if your RS is extremely large, then you will not even go to the terminal states, you just remain in the other states, and you will see as much as possible not to go to the terminal states. And here in this one, so it depends. So there are different different types of policies which are used depending on your value of RS that you are basically using. So I will not really go into all those things basically. So there are a lot of algorithms to actually decide on the policies to find the optimal policy which needs to be used, right. But what we will see is, we will see one or two policies, even though there are a whole lot of policies which have been given for doing this. So we talk about what is called the finite horizon or an infinite horizon. Okay. A finite horizon means that there is a fixed time n. Okay, after that time n, whatever action you take, it makes no difference. Okay, the game is over at that point in time. So it's something like saying UH of S naught S1 up to Sn plus k is the same as saying UH of S naught up to Sn. So after Sn, whatever state you go to or whatever action you take, it makes no difference. So that is what is known as the finite horizon. If n is equal to 100 or some such thing, okay, if your n is very small, say 3, then it makes sense to move towards the goal. Otherwise, if n is equal to 100, you have a lot of time to go there. Okay. So what happens is that if you if it's infinite, then you take the same action from every state to go to the next state. Whereas if it is finite, the optimal action would change over time. Okay, so as you come closer to the time that the ending time, it would be what is called a non-stationary thing. Whereas in the case of infinite case, it would be a stationary. You will move from one state to another state, okay, and the policy is stationary in the case of the infinite horizon. So, how do you calculate the utility of the state sequences? Okay, we want to find the utility. So, what do you do? So, if you have two state sequences S naught, S1, S2, S dash naught, S dash 1, etc. Okay. So, if you begin with the same state S naught is equal to S dash naught, then the two sequences would be preference ordered the same way, okay, as the sequences. Okay. So, there are two ways to assign utilities. So, utility of S naught, S1, S2, etc. could be equal to R of S naught plus R of S1 plus R of S2, etc. So, this is the additive rewards. The second one is what is called the discounted rewards, where you are using a gamma value gamma, which is between 0 and 1. So, you are saying that S naught has a higher value and then it is being reduced. So, this is called the discount factor. So, if you want to find the utility, what you do is utility of S naught, S1, S2, etc. will be gamma t into R of ST, right, which gives you your utility in the discounted method, right, and this is less than the R max, gamma t into R max, obviously, okay. So, suppose we want to find the optimal policy, so that is the pi star, right. So, suppose if we take the sequence S1, S2, S3, right, and we find the utility of some policy pi as the expected value of this particular utility, okay, which we have over here, okay. Now, out of all the policies, if you find the one with the highest expected utility, you get what is called the pi star S. Okay, so pi star S will be arg max of u pi of S, right? So you can find the optimal policy over here. So once you find the optimal policy, what you can do basically is that you can calculate the utility of S. Okay, so when we say pi of S, or if we say pi of A and pi of B star and pi of A star, right? So whether you're starting at A or whether you're starting at B or whether you're starting at C, it doesn't matter really. So you can just write it as pi of star. Okay. So what you want is you want U of pi of star of S, right? So whatever we get as U of S is different from R of S basically. Okay. So these values are what is shown here. Once we find pi star, using that pi star we can find these utilities. Okay. So these utilities actually are will tell you what are the actions you need to take at the various points. So using these utilities, there are one or two algorithms which you can use, right? So the utility function U of S allows the agent to select actions by using the principle of maximum expected utility, right? Once you have the utilities at the various nodes, okay, you can use this information to get the maximum, the policy, right? So there are two methods basically which are used here. Okay, the first one is what is called the value iteration. So the value iteration is used for calculating an optimal policy. So how do you do it? So the utility of being in a state is the expected sum of discounted rewards from that point onwards. Okay, so what you do is that the utility of a state is the immediate reward for that state, okay, that is the reward R, okay, plus the expected discounted utility of the neighboring states which you have of this, okay. So you could say U of S is U of a particular state S equals R of S plus gamma into max of this probability of S dash given SA into U of S dash. So what you do is, for example, if you take U of 1 1, okay, so in other words you are taking the square 1 1, you can take for R of S of that, which is minus 0.4 plus gamma into max of, you have the utilities which you have U1 2, U2 1, etc. So we have these values available to us from this particular square over here. So we put those, plug those values into this, right, and we can say that we are taking all the neighbors of the node. So 0.8 into U12 plus 0.1 into U21 plus 0.1 into U11, right. So this is what represents the action up, right. Similarly, left would be this, the right down would be this, right would be this, etc. And if you plug these numbers from that into this, then you find that up appears to be the best action that can be taken. So this gives you the maximum value, and therefore the action that you take is up at that particular point in time basically. So yeah. So what you are doing is that you are using what is called a Bellman update, which looks like this: U I plus 1 of S is equal to RS, which is the reward, plus gamma into max of this particular value. So we just saw how you choose what is to be done, and this algorithm is called the value iteration. So you have the it given over here, okay. So you keep repeating this thing, and it will tell you what is the action which you need to, I mean, what is the state you need to move to, or the action whether you have to go up or left or right, etc. And finally, you can return the U, which gives you the final U, which you are actually looking for. So this shows the evolution of the utilities. Okay, so the utility obviously of 4, 3 is going to be 1 always. And then you have the other states, the utilities of the other states starts with low values and goes up and gets a fixed value, whereas some of them actually go negative, right? You can see that some of them go negative and then they go positive at first. Okay. So that is one method. You can also use what is called the policy iteration. So here what do you do? The policy iteration algorithm has these two steps. Okay. Given a policy pi I, calculate ui, that is u of pi I basically, the utility of each state if pi I were to be executed. Then you do the second step, which is called the policy improvement. Calculate a new policy pi plus 1 using one step look ahead based on ui. Okay, and then you keep doing these two. Okay. So you will be able to see when you do this that it's very much similar to updating the Bellman equations basically. So you find the algorithm given here. Okay. So you're updating the policy basically here. Okay. And once you find that it is unchanged, okay, suppose you find there is no change in your policy, okay, then you're going to come out of this, and whatever pi policy you have, you will be able to return that particular policy. So this is the policy iteration algorithm, equivalent to the utility, the value iteration, like the earlier one which we spoke of there. So these are the two methods that are used, and this gives you, in the case of policy iteration, how the error reduces, right? So this gives you the max error, and you find the max error reducing as the number of iterations go on. And then you have the policy loss, and the policy loss is also coming down. So policy loss is u of pi I minus u. So this also you will find comes down as you go, as the number of iterations go on. So we have shown one or two ways of updating the utility of the policy. So there are a lot of methods. So what we do is that in every iteration you are going to take all the states and you are updating the utility or policy of all the states. But there are algorithms where in each iteration you can just pick a subset of the states and do some kind of updating. Okay, one of them, either value iteration or policy improvement, you can do just to a subset. Okay. So if you do this type of algorithm is known as the asynchronous policy iteration. There are many places where you can show that the asynchronous policy iteration is guaranteed to converge to an optimal policy. So what you find is if you have the freedom to choose any states to work on, you can design much more efficient heuristic algorithms, okay, where the algorithm concentrates on updating the values of states that are likely to be reached by a good policy, okay, and can also work on which is the subset of states that you need to use basically. So we'll stop at this point. So this is how we take complex decisions. So where we take a sequence of decisions. We also saw the Markov decision process and how the Markov decision process works for taking complex decisions. So we will stop at this point, and in the next session we'll talk about learning basically. So we change the topic completely and we talk about learning algorithms in the next session.